That was loud last night.
All
I could not.
right. Lexi's here, Allie's here, Kevin's here, Mia's here. Nobody's ever seen Raquel, have they? I don't even know who that is. Neither do I. All right. Yailin's here. Twyla's here. Trinity's absent. Jacob's not here. And Angel's here. Okay. That's
Were you
good.
study yesterday?
Beautiful.
When have I ever studied?
You said you were to do something for school.
The first day of school I was studying.
Y'all ready?
Sure.
You got a phone? Go to Psalm 19. Got a Bible. If you have a choice, go to ESV, just because that's what I'll be reading. Okay.
Psalms what?
19. Psalm 19. Do me a favor, once you're ready, just look up at me so I know. Psalm 19. The heavens declare the glory of God. The sky proclaims his handiwork. Day to day pours out speech, and night to night reveals knowledge. There is no speech, nor are there words whose voice is not heard. Their voice goes out through all the earth, and their words to the end of the world. In them he has set a tent for the sun, which comes out like a bridegroom leaving his chamber, and like a strong man runs its course with joy. Its rising is from the end of the heavens, and its circuit to the end of them. And there is nothing hidden from the heat. We'll stop there. So, the first section of that psalm, anyways, is, good morning, sir, is making this proclamation that when you look up, you simply look up at the heavens. It's proclaiming the glory of God. Okay? So when you look at a sunset, when you look at the stars at night, when you look at a fierce storm, when you see trees, when you see clouds, all of these things are speaking, as it were, on behalf of God and showing you something of his glory. I say over and over again in this class, you're a miracle. You should not exist. All the laws of the universe say that you should not be here, and yet here you are. And, you know, all just the things of this world, you know, if the earth didn't have the magnetic core that it does, if the core of the earth wasn't spinning, creating these magnetic field lines, then you'd get blasted by solar particles which would just destroy you. But that doesn't happen. If the earth was not tilted at this perfect angle compared to plane that it goes around the sun in, we wouldn't have the seasons. You would live in permanent ice or permanent like blazing heat or permanent sun. It would be a mess. There would be no changing of seasons. There wouldn't be the weather patterns that we have. There wouldn't be the beauty that we see. You know, they're searching the universe looking for habitable planets. They've never found anything like Earth. I mean, it's literally perfect. And you think about that, out of all that exists in creation, and here's this one place that is perfect for us to live. And that psalm is proclaiming that all that we see is telling us about the glory of God, the weightiness and wonder of who he is, and his goodness, and his power. I don't know, it just is mind-blowing. So today we're going to be back into biomolecules. And we're going to look at some thing. It's like, who could conceive of this to where life could exist? We're going to talk about phospholipids. And just when I say lipid, you ought to know, like, okay, that's hydrophobic. But a phospholipid is not entirely hydrophobic. Why on earth would there be this polar part? How do you get an enzyme to put the polar part with the non-polar part to where it forms this really weird shape? But if it didn't have that really weird shape, you would never be able to get a cell. Never, ever, no, not ever. But you gotta have that enzyme to do that. And where did that come? I mean, when I say that you're a miracle, I mean you're a miracle. You can't just put the parts together in a lab and make life. They've been trying this for coming up on a century. You can't do it. You can't even get close. You truly are a miracle. And everything around you, if we just stop to look and think about it, really does give us an awe of God. And so as we talk about all the details and all this stuff, and I'm just trying to pound knowledge into your head as fast as I can because there's a lot to cover, I would be a fool if I didn't take 5 minutes every now and again just to talk about something like this. Okay? So I want to pray, and then we'll dive back into these macromolecules. Father, thank you for how good you are to all of us, how you have given us this planet that is perfect. Set it at just the right distance from the sun, just the right tilt, just the right composition of atoms and molecules, and how it spins, and how it has a magnetic field, and that protects us. How you give us seasons, how beautiful everything is. You've not only given us life, you've given us goodness in that life, that we might be in awe of you and perhaps seek after you and know you. I pray that for each of these. Father, I just pray that even today, in the details of this, that they would see your mighty hand. Please help me to teach well, to make things so clear for them. And please help each of us as we're studying this, help to just saturate our minds and our hearts and help us to remember the things that we've learned. We pray this in Jesus' name. Amen. Well, real quick, we talked about 4 classes, 4 major groups of biomolecules. Can anybody name some?
Carbohydrates.
Carbohydrates, good. Give me another word for carbohydrates. Another word for carbohydrates. No? No.
Carbs.
Carbs. What do we call those? Sugars. Okay. Carbohydrates we tend to call sugars, right? So if you think about buying sugar at the store, you know that's a carbohydrate. Okay. There are lots of them, right? Some of them very, very important biologically. Some of them not as much. Okay, so we have carbohydrates. Can we name another? I've heard one already. Lipids. Okay. What characterizes all lipids?
They're hydrophobic?
They're hydrophobic. That's the one thing they all have in common. And we didn't finish lipids. That's where we were last time, and we'll pick back up. The one thing that all the lipids, because it's kind of a broad blanket catch-all category for anything that's hydrophobic, anything that does not like water. Now, let me ask you this follow-up question. The reason they don't like water is because they have a whole lot of 2 elements bonded together. What are they? No, elements. So think individual atoms of a certain type.
Hydrogen and carbon.
Hydrogen and carbon, those 2 form non-polar bonds. Non-polar molecules are hydrophobic. Guys, somewhere write some version of that down. I would expect to see something like that on a test for sure. We've talked a lot about electronegativity and polar and non-polar, and how if I have hydrogen and carbon bonded together, it's a non-polar bond. It makes it a hydrophobic molecule. You've got to know that. It is so important that chemistry and that set of physics is so important for our biology. If they didn't do that, you can't exist. Okay, so we have lipids, and I heard one listed already. I heard about fats. You know, their direct counterpart would be what? Say oils? Oils, fats and oils look very, very similar. Structurally, they're very, very similar. You've got a phosphate group, or excuse me, you have a glycerol group, which can make 3 bonds, and so they get 3 chains of fatty acids. If that chain is straight, no kinks, no curves, that's a fat, okay? And it's saturated. It's saturated with hydrogen. You can't put any more hydrogen into it. But now if I took some hydrogen out, it will double bond, and when I do that, changes the geometry of that molecule, and it will go from being straight to being kind of kinked out, okay? And that will make it an oil. And because it's kinked out, it can make fewer van der Waals forces, which means it flows better. That's why an oil is an oil at room temperature. It's a liquid. Whereas the ones that are like this, they can pack very, very tightly together and have more van der Waals forces, and therefore they tend to be solid at room temperature. Okay? And none of that should be new if you've been here the last couple classes. We've talked about those things. There's also waxes, and there are steroids, and there are going to be phospholipids that we'll talk about here in a minute. Okay, what are the other 2 groups, major groups of biomolecules?
Proteins.
Proteins, right? They're made up of amino acids. They form into a chain. We'll talk about them later today, Lord willing. And then the last group are nucleic acids. Name the 2 nucleic. There are only 2 macromolecules of nucleic acids. What are they? DNA and RNA. Okay, good. All right, now let's go ahead and dive in here. Let me get this set up to record this whole thing. All right. So we're going to go to where we were. We got a lot to cover here. Okay. I believe this was the actual slide we were on. Okay. Waxes. Waxes are long fatty acid chains. You don't need to know all this, okay? By the way, let me remind you, this is up on the Moodle, okay? So anything you missed, there's a video of last lecture and there's this. Not everything in this has to be memorized. This has way more information. Your book has way more information than you have to memorize. I will always highlight to you the key things, okay? Especially when we get into like the nitty-gritty here. Long fatty acid chains, esterified to long chain alcohols. Key thing is they're hydrophobic. These are for protection, right? Waxes on leaves, they protect leaf from losing water. Wax in your ear protects you from little water, but more importantly, maybe little critters that would try to get through and all that kind of stuff. Okay. Then we come to this idea of a phospholipid. And this is, okay, be ready, okay? Here we go. I'm going to first draw what we call a triglyceride. These are your fats and your oils, right? So triglycerides, you probably already have a drawing of this. I'm probably going to misspell this. I can spell this. So a triglyceride has a glycerol molecule, okay? 3 bonds, very readily. So I back to a fatty acid chain, okay? So it kind of looks like this weird, ugly jellyfish thing, right? You guys with me so far? Now, how many bonds does glycerol want to make? 3. That is very, very significant. All right? Because I can come along with an enzyme, all right, and I can remove one of these and add a phosphate group to it. Now I'm going to draw a phosphate. This is going to be my glycerol again. Let me double check that. Does phosphate have a -3 charge? Check it, Google it. Charge on a phosphate. Why does that matter?
Because it's gonna be even, the charge is gonna be even.
Speak up.
The charge is gonna be even.
How do you mean by that?
Because it wants to make 3 bonds.
Okay, so it's made its 3 bonds, right? It's got a bond here, and a bond here, and a bond here. I want to know why this having a charge matters. Do these have charge? Polar or non-polar on these? Non-polar. These are hydrocarbon chains. These are fatty fats, right? So these are non-polar. This section, whole section right here is non-polar. Okay, in fact, I'm gonna erase that and do that in green so this is easier to see what's going on. Okay. So this whole section right here is non-polar. Non-polar. Is it hydrophilic or hydrophobic? Huh? Phobic, hydrophobic. This does not want to be near water. Does it want to be around anything that has a charge? In any way, shape, or form? No. If I take oil, fatty acids, right? And I put them with water, do they want to be near each other? No, they will separate, right? You can shake them up and let them sit and they will separate. And that's not just about density. I pour sugar into water, sugar is more dense than water, but it mixes, right? And so you don't get a sugar layer and a water layer. But with oils and water, you get an oil layer and you get a water layer. Not just because of density, but primarily because one is hydrophobic and one is hydrophilic. They don't like to be near each other, okay? And then I put this with a -3 charge. Is that polar or non-polar? That's polar. Hydrophilic or hydrophobic? Hydrophilic. Okay, so far so good. It's okay, you're fine. I was just wondering if it was this. Okay, these 2 parts want to be near other non-polar things. This part wants to be near polar things. Do they want to be near each other? Yes or no? No. They can't stand each other. They want to be as far away from each other as they possibly can. Okay? Which means it's not going to stay like this. Okay? It's going to do this. It's not PO4, it's PO3. I just, sorry about that. We don't draw these every day, all year, for years. I'm just gonna mess up. All right. So now I've done what they want to do. I've separated the hydrophobic region from the hydrophilic region. It's literally like magnets, guys. They move apart. They don't want anything to do with each other. Okay? This has no charge. This has charge. This part wants to be near water. This part wants to be away from water. And so do you understand how I took glycerol with 3 fatty acids? It's a triglyceride. I took off 1, okay? And I added on a phosphate group, right? But that phosphate group doesn't want to stay near these, and these don't want it to stay. And so it all it has to do is just rotate, and it can do that, right? Because it's just a simple bond. It can just rotate 180 degrees. That's all it does, and you get this. And now things are happening. So far, so good? Okay. What biological molecule would help me to take off one fatty acid chain and add on a phosphate group? What molecule would do that? Just encourage you. Read your book. Review your notes before you come back in, okay? I know that we're not doing that. It shows. I can't reteach everything every class. You guys have got to review stuff. So an enzyme, an organic biological catalyst that helps to speed up and carry out chemical reactions by lowering the amount of energy that has to be put into them. An enzyme that's a protein would come along and it would take off one of these. You have different enzymes. You'd have one to take off a section that's called catabolism, and you'd have another one to put this on, that's anabolism, and that matters. And then you go from a glycerol to a triglyceride to what we call a phospholipid. It gets the phosphorus or the phospho name from this phosphate group. Now, biologically, this is extremely, extremely significant because when I put this in water, what happens is these want to be near each other and they want to be away from those, and those want to be near each other and they want to be away from these. And I'm going to represent this one more way, okay? I can take this exact same molecule and I can make it look like this. It's just a drawing, right? But this is really helpful. We'll draw it like this, okay? And we'll call that a phospholipid. Right? Now, when I put a phospholipid in water, what happens is all these phosphates want to be near each other. And all these long lipid chains want to be near each other. But they don't want to be near the phosphates, and the phosphates don't want to be anywhere near the lipids. So they're just attracted to each other. It's very, and there's water out here, right? Don't forget that. There's water everywhere out here that helps even with this to bind the charged parts together. And these want to get away from the charged parts. So that's good. So far, so good? Do you understand why it does this? Questions? This is all charge and shape. This is same two words, right? Because of the charge and shape, these want to be near water, these want to be away from water. These want to be near each other. But if we're in water, then they'd be surrounded by water everywhere, right? Including on the inside, wouldn't they? So what do I have to do to get these away from water? They need some on this side too, don't they? And so that is what happens. I'm just going to cheat, okay? Does that make sense? Now I keep all the hydrophobic things away from water. I keep all the hydrophilic things near water. How many layers do I have? 2. Greek prefix for 2 is bi. Okay? A 2-layer, a bilayer, and it's made out of, what are these called? Phospholipids. So this is a phospholipid bilayer. Okay. You need to draw that. You need to label that. You need to understand that. You need to understand the physics and the chemistry of why this happens. If this doesn't happen, you don't exist. There could be no cell. This is what your cell membrane is composed of primarily, is a phospholipid bilayer. If this does not, if the physics of the created universe do not dictate this, it doesn't happen. just realized I drew that whole thing in a section that anybody watching on the video can't see. So I'm going to draw it one more time while you're drawing it. That's what your cell membranes are made of, a phospholipid bilayer. There are other things that are in there. There are proteins that are in there. There's cholesterol that's in there. Sugar's attached to that sometimes, and all this is very, very important, and we'll dive into it much later. Right now, the key thing is your cell membranes are made of phospholipid bilayers. Phospholipids, just like a fat or an acid or an oil, except you take off one of those chains and you replace it with a phosphate group that takes something non-polar, turns it into something polar. So now I have a molecule that has a non-polar, a hydrophobic part, and then a polar hydrophilic part. Those parts don't like to mix. Literally, guys, if you took a bunch of these and you put them in water and you shook that joker up, it would form this. Now, if I extend this little lipid bilayer out in all dimensions, what shape am I going to make? A ball, a sphere, right? So I'm going to, there's a name for this. This happens. You can do this in a lab, no problem, very easy to do. It's called a sphere. It's actually called a mycele. Okay, and all it is a sphere of phospholipids. Phospholipid bilayer. There's nothing to it. This is just how God has made the universe. Because of charge, because of shape. This all happens. You change the charge, change the shape, change the electronegativities of hydrogen or of carbon, and you cannot exist. You cannot. Just as surely if the Earth were closer to the sun or further away from the sun, you could not exist. Just as surely as the tilt of the Earth, if it was changed by a degree, either direction, life on Earth could not exist. But here we are, killing it, because God has made us this way. All right. So that's that, right? That makes sense now, doesn't it? Do you understand that this is, how many times have I told you that this is important? This is not going to go away. This whole first semester, by second semester we'll be on to some other stuff, but this whole first semester, this does not go away. You must know this. That whole charge shape thing from day one, here we are in week 3, the end of week 3, like, it never goes away. All right. Yeah, that's the same thing. That's what we just drew, right? Okay. They use the word amphipathic. That's a fun word. I don't need you to memorize the word, because sometimes it's called other things. Anyways, sometimes it's like amphoteric. But I do want you to know amphi or ampho. It means double. It means double. You encounter this. There's a whole group of vertebrate animals. That particular group has amphi in the top label of it. Do you know what it is?
Amphibian.
Amphibians. Name an amphibian.
Turtle. Tortoise.
No. do live in the water, but they're not actually an amphibian. They're just a straight reptile. So, but a frog is an amphibian, right? What do you know about frogs?
They're nasty.
They're nasty, okay. What else do you know about frogs?
They start in the water and
They start in the water, they lay an egg. When that egg hatches, what does it look like? It looks like a little fish, right? A little tadpole doesn't have legs. It has little fins. And then it changes. Those fins go through a metamorphosis and they become legs. And then that thing that had to be in the water now can live life up on land. And so it has a double life from water to land, hence amphibian, okay? Double life. In this case, amphipathic or amphoteric, double-sided, double structure, double charge, double everything. One polar, one non-polar. So amphi is one of those just really, really useful Greek prefixes, okay? Worth knowing, definitely. The next group of lipids, that's where we're at, right? These lipids. The next group is steroids. You want me to sing for you? Yes or no? You don't seem real excited. Okay. This matters later, this song, but it has something very useful right now. Hormones are chemical messengers, hurrah, hurrah. Steroids include estrogen and testosterone, amino acids, insulin, take up that glucose, make glycogen, so you don't die of a diabetic coma while you're all alone.
One more time,
right?
one more time.
All right, no, that was not. Okay. Hormones are chemical messengers. That's really, really useful to know. All a hormone is a chemical message. But there are two types of hormones. Hormones are chemical messengers. That's like the theme of that song. Then the first group, steroids, include estrogen and testosterone. So estrogen and testosterone, not only they're hormones, but they're steroids. So whatever's true of a steroid is going to be true of estrogen and testosterone. I like to, whenever I can, connect some of these things to your real life, right? So when you hear estrogen or testosterone, you know it's a chemical messenger. You know that there are two types of chemical messengers once you learn that song, and one of the group is going to be a steroid. Steroids are lipids. It's 4 fused carbon rings and usually other tricks happening. So you've got a picture up there. You don't even need me to draw this, but I'm going to do it anyways because it's fun. I like to draw and I like to sing. What are you going to do? You're stuck. It's kind of like drawing soccer balls, right? The guys in the back, I hope you get a kick out of this. So. Then, you know, it's got some stuff up there. So they look like this, more or less. The key thing is, at these vertices, you're looking at lots and lots of carbon, okay? Carbon like everywhere. And off of that carbon, lots and lots and lots and lots of hydrogen, right? When I see carbon and hydrogen, what do I know? What? No, you were giving me like oxygen and hydrogen. I want to know carbon and hydrogen. Non-polar, hydrophobic. These things don't like water. You put a bunch of steroids, estrogen or testosterone or cholesterol in water, they're not, and I could shake them up, they're going to form a layer, right? They're not going to stick with the water. But you know what is cool? I could take one of these. I'll just try to draw quickly as I can. I wish I was better at this. You don't have to draw this part, okay? And poor people watching on a video aren't going to see this part. That's a, well, maybe I can make this. Here. You can stick these in your phospholipid bilayer. And they are. There's actually often a lot of cholesterol in your phospholipid bilayer. Let me make it so they can see this. So this is all hydrophobic. You stick it in your water, it wants nothing to do with it. But I can stick it with other hydrophobic stuff, like in the midst of a cell membrane. Now, look at, if these things, by the way, these can like bob and move very, very freely. It's like an oily layer there, okay? The two layers move independent of each other all the time. But when I get this cholesterol molecule, I wish I'd have done it in color. Wish I'd have thought of that. Maybe I'll just color it in real quick, okay? When I stick a cholesterol molecule in there, that's like a speed bump. You ever go, cruising down the road and all of a sudden there's a speed bump? What do you have to do? Yeah, you don't have to come to a complete stop, but you better slow down. You're going to do some damage. These are like speed bumps in the cell membrane. They slow down the flow of that molecule. As the molecule gets hotter and hotter and hotter, as a cell in an organism gets hotter and hotter and hotter, these things flow faster because of the energy. I don't want them to flow so fast they flow apart and break, so I might want to add more cholesterol to it to slow it down. And that's what happens, by the way. Organisms in the summertime will have more cholesterol in their cell membranes. And in the winter, you don't want them to freeze so they don't move, so you take out the cholesterol so that they flow more freely. Isn't that amazing? How do they know to do that? Who could conceive of something like that? And yet you're not sitting there thinking about it, you're just doing it, right? And other organisms are just sitting there doing it. Pretty cool stuff. Okay, let's see. Let's go back to the split screen. Let's go back to this. Here we go. Oh, gotta put back up. Okay. They're hydrophobic, they're insoluble in water, cholesterol is the most common, they're synthesized in the liver, precursor to all kinds of stuff. There are 3 of these I want you to know, okay? 3. I've named them all. What are they? No, I'm sorry, 3 types, 3 examples. Hormones are chemical messengers, hurrah, hurrah. Steroids include estrogen and testosterone. There's 2, estrogen and testosterone. Somebody walking by is going to go, what is that fool doing? Okay, so we've got estrogen and testosterone, and there's one more I've talked about it a whole bunch. I've drawn it. Cholesterol, estrogen, and testosterone, and cholesterol. Okay, you must know those 3. You must. You will hurt my feelings if you don't, and I will hurt your feelings with a test grade if you do that. You're bad. We'll all be sad. All right. Okay, this is cool stuff. I love talking about proteins. I want you to do that first. I get pumped doing this. When I left teaching, people would ask me, do you miss teaching? And I was like, I miss students, I miss certain things, but I didn't miss like the institution of teaching. Like, I was so happy to be out of the system. I just adore you guys, and I adore doing this. And it's these few weeks already have just been a lot of fun.
What you teach?
This.
No way.
Oh, Las Vegas.
Right?
Born and raised. Do you know where the other Las Vegas is? In Mexico. Been to them both. I was born and raised there. Okay. Y'all ready with this? Okay, let's erase it. New theme, we're on to proteins, okay? Okay, proteins. They do all of that. Regulation, structural, protective, transport, enzymes, toxins. They do all that. You need to know that. It would be very fair for me on a test to go, hey, which one of these does a protein not do? And then I'll replace one of those with something else, right? Or in an essay to go, tell me what a protein does. I will just remind you, this is already up on the website. Super easy. You can still do what you want with the phone or whatever, no problem. But just, it is there. So there you go. Okay. My drawing is not so much, you know, these works of art here. Proteins do so much for you. Let me draw a protein. Make sure anybody watching the video can see this also. Well, apparently I reversed what I was doing and I didn't remember it. This is the side they've been able to see all along. Okay, well there we go. So, take a look at this phospholipid bilayer, right? What am I drawing here? What is this? My phospholipid bilayer has become a lot more than just a phospholipid bilayer, hasn't it? It's become a cell membrane. So in this cell membrane, I've got my phospholipids, I've got cholesterol, and now I just put in a protein. And check out this protein. This particular protein that I just drew, and I'll try to make it a little darker. Notice something about it. Does it look like one protein or two?
Two.
Looks like two. And what do you notice? Why does it look like two? Because it looks like you could pass something through that, doesn't it? And you need to be able to pass stuff through your cell. There are a number of ways that that can happen, but one of the most important ways that that can happen is through a protein, a gate or a channel, right? Transport. You can also have them attached here that do enzymatic activity and stuff like that, but your cell membrane is amazing. Dare I say, it's a miracle. This is what God has not done to make you use so that you can live. It's just mind-boggling. Do you guys have all this down? You feel good here? Gentlemen in the back? Feel good here?
Good.
Okay, I'm going to roll this forward then, okay? So, all right. Enzymes. We talked about enzymes last time, right? And I guess I've got to get rid of my beautiful drawing here. I'm going to go ahead and take this away, okay? I don't know about this. Not that you would do anything. That's rough. Oh my goodness. Here we go, clean slate. So, some proteins are enzymes, and some enzymes, I'm sorry, all enzymes are proteins, right? I think we probably did a Venn diagram last time, right? Some proteins are catalytic, or catalysts. Some catalysts are proteins. Where those two overlap, we call those enzymes, right? So that's the thing that we're going to be looking at here. I will call him that later. Okay. So enzymes, catalysts in biochemical reactions. I think we just said these are biological catalysts. They speed up chemical reactions. They reduce the activation energy required to make something happen. And there are 3 types. Okay? I don't know why. I'm not worried about that catalytic. Let's learn catabolic and anabolic though. Okay? You ready for this? Everybody see where I put them? There we go. Let's do catabolism and anabolism. Actually, let's do metabolism first. Metabolism. This is, by the way, this is kind of a sub, like we're stepping away. Let me slow down my words, I'm ahead of myself. Our theme right now is proteins. Our sub-theme is enzymes, but we're actually taking a side step from enzymes so that you can understand a little bit about metabolism, about catabolism and anabolism, okay? So metabolism, right? Metabolic activity, you've heard of this, yes? Okay, this is simply the rearrangement of biomolecules. That's it. Okay? You say that's it. It's a very, very big deal. Sometimes, actually oftentimes, you eat something, right? You take in food, but you can't just take broccoli and be like, okay, go run. That does you no good. You eat the broccoli and you can't get the broccoli into your body. Even after you chew it, you can't get the broccoli into your body. What do you have to do? You have to break it down into smaller pieces, right? That's metabolism. Breaking something down into smaller pieces so that you can use it. That is metabolism. It's a specific type of metabolism. It's called catabolism. Breaking down. And the other type is where you're building it up, okay? And that's anabolism. How are you going to remember the difference between catabolism and anabolism? You have to remember certain things about cats. Cats are evil little creatures. They're no good. So if you were building something out of Legos, like a little Lego tower, and you left the room, what's going to happen? That evil cat is going to come along its fangs, its whiskers, right? And it's going to take its ugly paw and it's just going to smash through your Legos and break them all into pieces. Because cats like to do that. That is catabolism, okay? And then, how are you going to remember anabolism? You think of your friend Anna, who is so sweet and kind. And traditionally when I've drawn Anna, from the very first time I did it, I was drawing so fast that she had like one arm and it was sticking out of her mouth. So Anna's like doubly disabled and all this, but she's so helpful. And so she comes along and she helps you build these back into a tower, right? So here's Anna. She's happy. She's nice. She's got long hair, I don't know, from like the 60s or something. And she's helping you build it back, right? So that's Anna. Okay? So we have Anna and the cat. Anna is helpful and she builds things. You want the rest of her body? What do you want out of me, guys? Not that good. So, Anna helps you build, and the cat destroys. Catabolism and anabolism are 2 types of metabolism. This is happening in your cells all the time. You eat something, you have to break it down into its parts, and then you have to be able to put those parts back together in a form that you can use, in the forms that your cells need. You do this all day, every day. If you can't do one of these steps, we tell you that you have a disease. We tell you you have a metabolic disease. Usually these metabolic diseases come from genetic mutations. So it's a genetic metabolic disease. You get the wrong genetic metabolic disease to where you can't do one of these with something that's incredibly crucial, and you die. Most of the miscarriages and stuff are because, you know, that little baby has something wrong that it can't do, either catabolism or anabolism. There's something wrong with the DNA, which means there's something wrong with the RNA, which means there's something wrong with the proteins, which means there's something wrong with the enzymes, which means that they can't do this. So they can't sustain life, and they will die. This happens all the time, unfortunately. It happens in lesser degrees in those of us who might seem healthy. Somebody who is lactose intolerant, you can't do this. You can't break down lactose into its two parts. And so it passes through you undigested, and then like little bacteria in your gut, which are good. You need bacteria in your gut. They do useful things for you, like producing vitamin K that you can't make for yourself. But they take that lactose and they have a field day with it. And they start going crazy and reproducing and doing tricks, and they produce a lot of the gas. Think about that. All right. So, enzymes, right? They do metabolism. We have the two types. You got it, Anna and the cat. Good. Okay, so catabolic, anabolic. Let's go to the next slide here. Okay. Wow. That's thorough. That's cool. You don't need to memorize that. That's too much. All right? So digestive enzymes. Let's talk about 2 or 3 of these in particular, okay? Where does digestion begin in your body? You eat a piece of bread, where does it begin? It begins in your mouth because you have an enzyme in your saliva called amylase. Amylase breaks down starch into glucose. If you just spit on a piece of bread, it will begin breaking down. That's cool. It's also kind of gross, don't do that. But there is a lab that we normally do where you spit into some starch, and we test the starch with iodine. So starch with iodine will turn like black, okay? So you'd have a control where you'd spit into just a starch, or I'm sorry, where you just have a starch solution and put some iodine, it would go black. And you take that same starch solution, put it in a tube, test tube, and you'd spit into it, and you'd shake it up, and we'd come back 10 minutes later, and you'd put the iodine, and it wouldn't become black. Well, why is that? Because the starch is all gone. Where'd it go? Well, the enzyme, the amylase in your spit, broke it down into glucose. And that's super cool. Another one is called pepsin. Pepsin does the heavy lift. You know that stupid song, I Came In Like a Wrecking Ball? Okay. You want me to sing?
Yeah.
I'm not going to do it. Pepsin comes in like a wrecking ball. Pepsin is, you know, in life there's a difference between like a scalpel and a hammer. They'll both tear stuff up. But a scalpel's like, you know, for precise things. And a hammer, you just tear stuff. I mean, Pepsin just comes in and just cuts proteins and other things into these chunks, right? It's big. It's in your stomach, okay? You ever heard of, what else is in your stomach? Lots of it, lots of it, lots of it. Acid, right? So here's something that's really cool about Pepsin. It doesn't work unless there's a lot of acid in your stomach. It cannot function. It's God, think about this. God made this enzyme that's like so critical in your digestive process and has to live in an acidic environment to where it can only work in an acidic environment. It can't work otherwise. Most proteins, you put them in your stomach, they're just gonna, you know, that's why your stomach's so great. You can, okay, you ready for this? Out of the trillions and trillions and trillions of cells on or in your body, what percentage, I don't mean of mass, but I mean of individual cells, what percentage do you think are yours? the bulk of you is human, okay? The bulk, not all of you, but the bulk of you is human. Because your cells are really big, and other cells maybe are really small. So I just want to know if we were to count all the cells that are not yours and all the cells that were yours and did a calculation of what percentage of the total cells are human. Now the trillions and trillions on or in your body. Can you guess?
20.
Less than 10. You are so greatly outnumbered. Now you're bigger, but you're greatly outnumbered. Are you brave? Lick the back of your hand. No. That bacteria is delicious. You are covered in bacteria. You just don't know it. I mean, it's like everywhere. Just want to gross you out a little bit. They're all over you. They're lining your stomach. They're all over your skin. You know where you don't want them? In your blood. That would be bad. You don't, you're like, take a second here. Here's you, okay? I'll draw you kind of like a gingerbread, okay?
Oh my god. Oh.
This is going to be useful, okay? All right, so here's you, all happy like the gingerbread man, okay? You have a hole right there. That hole goes somewhere. Where does that hole go? Down your esophagus into your stomach, right? All right, and from your stomach, where does it go? Small intestines, and then to the large intestines. So I'm just going to have this kind of, loop a little bit. That's good enough. And then where does it go? Where does it go?
Your liver and your kidney.
No. If you eat some food, you got a hole that it goes in. It goes down, it goes into your stomach, goes through all these intestines, and then it goes full of a piece of corn.
Toilet. The toilet.
Yeah, it goes to the toilet, but it has to come out of a hole. Just waiting on you all. There's not an unexpected response. Here's why this matters, okay? I should have drawn you like sideways here. We'll do it like this. That'll help. Visual. Okay, here's your lips. Having a bad hair day. It's like Pigpen from, or you guys probably don't even know that, from Charlie Brown. All right, so anyway, or Pigsty. So food comes in, stuff comes in, it goes all the way down, and then eventually it goes out, and you hope that that if you were brave and you licked that, you hope that any bacteria that survived did not make it into your body. You hope that it went all the way out. So I'm telling you that this, especially down here, is just lined with bacteria. And you need it to be. But what you don't want is that bacteria to get into your body. And you don't want any other pathogen, any other bacteria, virus, whatever, to get into your body. But you're getting it in all the time. You're breathing it in. You ever go to a pool? You ever drink water? You eat something, you shake hands, you're not thinking, you're my little kids, and so you're just constantly doing this, and you're just flooding your body with stuff that would love to kill you. But because you are so amazing, and because your God is so amazing, your stomach makes acid, right? Acid, which kills so much of it. Not all of it, but so much of it. So you've got this enzyme called pepsin that has to work in an environment that's highly acidic, that's killing everything. But your enzymes survive and theirs don't. That's amazing. Okay. Y'all didn't draw that? You're not taking a picture of that? We'll move on. Okay. So, all right, we talked about amylase, we talked about pepsin. There are Hemoglobin, you've heard of that. That's in your blood. It transports oxygen. That's its one job. Structural proteins like keratin in your hair or your fingernails. Hormones. Hormones include
Testosterone.
estrogen and testosterone. We got to work on that one. Defense in your immune system. All right, let's move forward. So amino acids. Somebody tell me what time it is.
31.
Okay, great. So amino acids. Where does that name come from? It's got two parts to it, right? Amino and acid. Right? So let's draw it. Always has a central carbon atom. This is a carbon, this is a carbon. This is going to be to an H. This is going to be to what we call an R group. I'll explain that more in a minute. And then we go to the acid part. I'm gonna do it like that. Do yours like that too, okay? With kind of a dotted line, because that'll explain that. Oh, I drew that wrong. I'm sorry. I drew that wrong. That's my fault. Draw this one dotted. I actually really like how they did this. They did a good job on this diagram.
Is that supposed to be a nitrogen? Is it N?
Yes, what did I draw? I drew a carbon. That was done. Thank you, Jacob. Appreciate that. Do you know that in Japan teachers deliberately mess stuff up? Because it challenges the students. In America, we get so you get used to being spoon-fed everything, and then when things get hard, you tend to quit. In Japan, they intentionally keep the pressure on, and they'll even have the teachers mess up the problems because it keeps the students constantly on their toes. I can imagine it might get exhausting, but they do score a lot better in math and science than we do. And one study thinks that that's why. Like they went and watched what's different in the classroom. So anyway. You're welcome. Okay, this is an amino acid. It has two parts. It has an amino part and it has an acid part. Okay, so let's look at the amino part. That's this part right here. So there's a compound molecule that you're all familiar with. It's NH3. We call this ammonia. Ammonia is NH3. The functional group, NH2, is what we call an amine group. Okay? See the connection in the name with the AM part? The difference between the two of them is just take off a hydrogen and then attach it to a carbon here, right? So this is an amine group. All of your amino acids have an amine group.
Bless you. Thank you.
This section over here is a carboxyl group, and the thing about a carboxyl group is that sometimes this, do me a favor, all pencils down. I just need you to hear me and let's get this in real quick, okay? The thing with a carboxyl group is This double bond with the carbon here pulls the carbon's electrons, and that makes the carbon pull this electron a little bit harder, and oxygen's already way out pulling hydrogen. And so this hydrogen over here sometimes will dissociate. It will form an ionic bond instead of a polar covalent bond. And that makes this an acid, because all an acid is a hydrogen ion. A hydrogen that's lost its electron, so it's a plus charge. It's a proton just floating around there. So that's why this is called an acid, right? Because this carboxyl group forms a carboxylic acid, which means that this will dissociate. So it's not a strong acid, it's very, very weak, but it's significant, okay? So that's where it gets its name from. Amino acid, okay? The other thing here that I want you to get is, this is called the central carbon, okay? Because it's just in the center. We got like 3 things. We got a central carbon. I got a hydrogen on one end, that's easy. On the other end, I have this R group, okay? Biologically, there are 20 different R groups, okay? There are more, biologically there are 20 of these. There are more than 20 in nature. There are more than 20 that we can make in a lab. Your body uses exactly 20 amino acids. We call them essential, right? If you can't make them, you have to get them. Because some of these you can't make, you just have to get, you have to ingest them. And if you can't make them from other things, then that's a metabolic disease, right? And that's because an enzyme isn't doing its job right. But in you, in a bacteria, in all of life, we use 20 of these, 20 different R groups. It could be anything from just an H, a hydrogen bonded there. It could be an OH, a hydroxyl group bonded there. It could be a methyl group, CH3 bonded there. It could be little, it could be big, but there are 20 of them, okay? Most amino acids, the bulk of amino acids is just like this. This is slightly charged, right? This, a little charge, not much to speak of. This has no charge, but this could be everything from a huge, relatively speaking, non-polar hydrophobic chunk to an extremely polar chunk. So by changing these, I change the charge and shape of the whole molecule, and I've got 20 of these that I can use in a biological system, okay? So the thing we want to know about this is that there are 20 biological R groups. I'm sure we're going to look at those 20, at what the 20 of those are in a moment. But you got to know that drawing, okay? I'm not telling you that you have to know, oh, that's nitrogen, that's oxygen, or whatever. But if I were to draw this, you better be able to label which one's the amine group, which one's the R group, and which one is the acid, okay? Like, no kidding. Does that make sense? All right.
Say it changes the charge and shape.
If I change this, I change the charge and shape. That changes what their function. I got 10 minutes. I feel like very long. Not when you're drawing cats and stuff, right?
It's pouring rain outside.
Is it really?
Yes.
Wow.
I was looking at time.
You can
I was
hear.
like, what the heck? I was like, it didn't say it's supposed to rain, but it's...
I can hear now.
Oh.
I mean, you like spoke and there it was.
Little St. Collins, the roof might flood and leak, so just fair warning. It does just been topped.
Like a lot?
All right, here we go. Amino acids have diverse chemical properties. 20 common amino acids commonly found in proteins. Each amino acid has a different R group. We talked about that. R groups determine the chemical nature of each amino acid. They're either non-polar or polar or positively charged or negatively charged or non-polar. They can be aromatic. Kind of weird to talk about that. Look at them. Look how cool those are. Look at that. That kind of almost looks like those steroids did, right? Like it's got these cool circles and stuff. That's tryptophan. You've heard of tryptophan. Where's tryptophan at? This is very un-American of you. Don't you celebrate Thanksgiving? Turkey. You never heard people talking about how you get a lot of tryptophan when you eat turkey and you get tired? No. Golly, I must be old. Okay. I've heard that all my life. All my life. You'll catch it now. You'll hear it on the news. You'll now that you've got that word in your mouth, you'll catch it.
Yeah.
This has a negative charge on it, so, I mean, my goodness, that wants to be around water or around fats? Which one? Negative charge.
Water.
Wants to be near water, hydrophilic. Oh, they've got them, this is a great diagram. They've got them labeled. So, polar, uncharged, over here. Non-polar, aromatic, right here. Negatively charged, positively charged, and non-polar aliphatic R groups. All right. You don't need to know, you don't have to have these 20 memorized or anything like that, right? Just, there are 20 of them. Notice some of them are simple, little, like just one hydrogen atom, and some of them are big and complicated, like tryptophan. Okay. More on amino acids. Amino acids are represented by a single uppercase letter or 3 letters. You don't need to know that right now. We'll get to some of that later when we do the central dogma. Essential amino acids. The following must be supplied in diet. So isoleucine, leucine, and cysteine. You can't make these. No human being can make these. You have to eat these. Okay? When it says essential, it means like if you don't eat it, you'll die. Okay? You can't make it. Period. Okay. And check out this. It says the sequence and number of amino acids determine protein shape, size, and function. So I assume the next ones we're going to get into. Oh, we're not getting into that yet. I don't know why. It seems like a good time. We'll do what it says next, though. You feel good here? Okay. You don't have to memorize those 3. Okay. It's a fun fact, but amino acid monomers are linked together via what's called a peptide bond. Yeah, it's just saying like, hey, we're going to bond this to that. Okay? You want me to draw that? Let's draw that. You know, let's do better than that. Let's find a video of that. I think I can do that. I got a few minutes. Let's do it.
It's gonna be raining like all day.
Electricity class. I
It was
hope,
stress.
no, you apologize.
No guarantees. I've not watched this, so it might be terrible. Or have nothing. I don't know. Okay, that was almost useless. So these are 2 different peptides. Monopeptides. They're monomers. Okay? And what happens is when using an enzyme, they're just drawing this out in space, that's not realistic. Using an enzyme, one is going to lose a hydroxyl group, an OH, one's going to lose just an H, and so when I take H and OH and put them together, what do we call that? Water, right?
Yes.
I have to remove water to link these 2 things together. What do we call that when we remove water to put something together? Dehydration. Synthesis. Y'all we gotta work on these things. We will. We'll get there together. Okay. See if I can get a better one.
Peptide bond, also called the eupeptide bond, is a chemical bond formed by joining the carboxyl group of one amino acid to the amino group of another. A peptide bond is an amide-type covalent chemical bond. This bond links two consecutive alpha amino acids, carbon number 1 of one alpha amino acid and nitrogen number 2 of another. This linkage is found along a peptide or protein chain. During the formation of this bond, water molecules are released. A peptide bond is usually a covalent bond. Since the water molecule is eliminated, it is considered a dehydration process. This reaction is also known as condensation, which usually occurs between amino acids. Peptide is a Greek word that means digestive. A peptide is a short polymer of amino acid monomers linked by an amide bond. During the reaction, one of the amino acids gives a carboxyl group to the reaction and loses a hydroxyl group. The other amino acid loses hydrogen from the NH2 group. The hydroxyl group is substituted by nitrogen, thus forming a peptide bond. This is one of the primary reasons peptide bonds are referred to as substituted amide linkages.
You never need to know that. You never heard that. So, here's what you do need to know about a peptide bond. Write this down. It's dehydration synthesis between the carboxyl group of one peptide and the amine group of another peptide. And that's it. It's how they're bonded together. It is the dehydration synthesis between the carboxyl group of one amino acid or one peptide and the amine group of another peptide. When I say dehydration synthesis, that means I'm removing water, right? I take off the OH here, I take off the H here of two adjacent ones, and I stick them together. And now my monopeptide becomes a dipeptide. One becomes two. And if I added a third one, then my dipeptide and my monopeptide would become a tripeptide. And past that, I would say that I made a polypeptide. All right. Each one made up of individual peptides, another word. I could say monomer, right? One unit. Okay, very good. All right, guys. That's good. We'll stop there for today. Okay? The Lord bless you and keep you in this rain. There's a psalm that says, "Let the redeemed of the Lord call upon His name at the right time. They surely shall not be overwhelmed by the flood."